So hi everyone, thanks for joining live, for folks who joined live today, and as well as people who will be watching the webinar later on YouTube. So this is a Multimodal Weekly, a virtual webinar series hosted by a startup called 12 Labs. For context, we an early stage Series A company building multimodal foundation models for video understanding. I've been doing this webinar on a weekly basis over the past almost 1.5 years or so. We tend to discuss a variety of topics, but we have a lot of researchers coming in and give talks about, at the intersection of multimodal AI and, foundation models. Sometimes we have developers who view interesting application in multimodal in different verticals come talk about their projects. And, we have founders and entrepreneurs talk about their respective startup as well. And yeah, sometimes web team members come in and give a talk about what's going on with our platform and our API. So in some of the recent session, we have researchers talking about different aspects of video, web team members coming in and talk about our recent development in our product as well. For today's session, we'll go back to the research route, and we'll have three researchers that in some form or another doing work, very interesting work in video understanding, multimodal understanding, etc. So the first speaker is going to be Ashmal Vayani, who's currently a master student focused on computer vision at UCF, University of Central Florida, and he will present his work called VURF, General Purpose Reasoning and Self-refinement Framework for Video Understanding. The second speaker is going to be Yujin Jeong, currently a PhD student at TU Darmstadt, and she will talk about her paper called ReWaS, right? Read, Watch, and Scream, sound generation from text and video, and abilities is the work you've done while collaborating with Naval AI Labs. And finally, we closed out the webinar with another PhD student from UC Santa Cruz, Diji Yang, who's going to give a talk about his paper called Dual Modal Distillation from action classification with hybrid edge cloud solution. And all this work has been published at the recent NeurIPS conference, and two of them, the one from Ashmal and Diji, I believe, was also at, being presented as poster session at our video language model workshop that the 12 Labs team calls. So yeah, super excited to have you guys come back here and give a virtual talk to our broader community. With that, just quick logistical note for the live attendees, feel free to send your question on the Zoom chat, and then we'll have a short 5-minute Q&A session after your speaker finish. So yeah, with that, I will stop sharing my screen and I will unmute Ashmal, and you can go ahead and present the screen and go ahead with your presentation.
Sure. Alrighty, can you guys see on the screen?
Yep, I can see it.
All right, okay. So hi guys, my name is Ashmal Vayani. I'm currently a graduate student at University of Central Florida, and my research work that I'm going to be presenting today, we did this when I was working with Mohammed bin Zayed University of AI, and this work was accepted at NeurIPS workshop on video language models, so we presented this year. And so the title of this work is General Purpose Reasoning and Self-refinement Framework for Video Understanding. So it's Video Understanding and Reasoning Framework, which we also call it VURF. It's completely open source, and you can have our paper and code access. We will give you access to that. So talking about the work, the motivation of this work is to understand, okay, the current video models that we currently have, they lack this general purpose understanding. They do excel at certain tasks, but they lack this generalization capability. And if we have to train a new model, and if we have to train a dedicated model for downstream tasks, we need to have certain data sets for them, and we need to have a separate training frameworks for them, which is again a bit expensive. So there is a need for some unified framework, which can again follow this approach of visual programming, divide this complex video tasks into some simpler tasks with the help of LLMs. Again, just to explain more on the problem. So the problem with this individual tasks is they do not generalize well, and they do not give you the complex comprehensive understandings of these videos for these complex reasonings. There is a need for a generic framework for that. And now the important question is, can we harness the utility and in-context learning examples of large language models to solve these complex tasks? So just a disclaimer, we don't use LLM, for video processing, we just use them as a tool for us. We're going to come back to it later. This is a general overall pipeline for our work. If you look at this, some video frames, there is something happening in this video, and dog is running, and the instruction, which is right there. Let me have this 1 second. Right, so the instruction is to track the dog and blur the background. And we have some in-context examples that goes to a self-refinement block. We're going to come back to it in some later slides. Along with the instruction, we pass them to large language models. And ideally, we expect large language models to output some visual program like this. And this visual program will contain some set of subtasks, which will be executed sequentially. And each result will be passed to the intermediate next step, such as if you have in video, the task is to track, and the query is that we pass the name of the object that we want to track, and this output we call as track 0. Now this track 0 is going to be passed to the next step, and the background blur is going to be applied to that. So the overview is we presented this first general video visual reasoning framework for video understanding tasks. And the good thing about the task is you don't have to train a new model. You can simply use off-the-shelf computer vision models that are currently available to you. And this is a plug-and-play architecture. We also leverage this in-context learning examples and capabilities of an LLM, where the task of an LLM is to decompose a complex task into multiple subtasks, which can be executed in sequence to achieve the final output. And the last is we have a self-refinement approach for in-context examples and for the program that's generated so that we can avoid some of the hallucination issues of language models. Again, coming back to the VURF pipeline, this is the overall pipeline that we have. We're going to be discussing that in the detail. The general pipeline is we have this input video and we have some natural language instructions and we have some of the in-context examples. The refinement block we're going to be discussing in a few minutes. And then in general, we have this LLM, some refinement block, and we have this high-level program. So essentially, this is how the in-context examples or in-context instruction program pairs looks like. Just like how we explore, we will have some videos and we will have some arguments, and it's going to be passed through a function. In this case, it's going to be function O, and the output of that is going to be passed as a preceding step to the function 1. And that's how its substeps are internally connected. In our work, we use GPT 3.5 to generate these visual programs, and we provide this in-context learning examples that we build and write for each video understanding task. Again, LM does not perform the video understanding task. It just formulates this logical sequence of flows so that it can decompose tasks into some complex task. Right, and the next we have this, when the LM outputs a program, we have this refinement plus self-correction module. So we know that LM can hallucinate. It can generate a program that's not exactly accurate. We have certain lists of modules that we limit to because ideally it can infinite to multiple tasks. It's just a plug-and-play architecture. You have to write in program interpreter and you should be good to go. But we limit to certain tasks like VQA and multi-video question answers and image editing, video editing and stuff. So it has to follow some module list and it cannot go beyond that. And the another possible solution and problem can be that the LLM does not break down the task optimally. So in this case, we pass that to the refinement block and it keeps on regenerating until you have the fine visual program that can be taken by the visual interpreter. And again, so whatever the high-level program we get as the output of the refinement plus self-correction model, we pass it to this program interpreter. And this program interpreter, along with this video input and the natural language instruction, it utilizes off-the-shelf vision language models that we currently have. So the best part of this framework is you can replace the current model with the best available state-of-the-art model, and it should work just fine. Now, coming to this refinement module, the refinement module we have is essentially something that we follow a process because the in-context examples that we write, we also have this LLM intervention to optimize them better. For that, we follow an approach. Initially, we have this instruction that we have from the datasets that we have, and then we try to give it to the model, which is again GPT 3.5, and it will generate a program with the usage of in-context examples. Then we take the same instruction, and now without this in-context example, we ask an LLM to generate a visual program. But again, we pass some of this structural complexity so that it does not go beyond that structure. We want it to follow certain steps. We do pass that. And now LLM is given both of these programs, one with an in-context example output and one without that. And it tries to realistically bring them together to have a one final output. And we repeat that with some n instructions, like with n times, and we have this final in-context example. So one of the example is this: we have a question at the end of the video: did the man in the blue jump, or in the man in the gray? So we pass some in-context examples and it generates a visual programming program. And then again, we pass the same instruction to an LLM without the context, without the in-context examples, and it generates another program. We combine and send them both along with this instruction to an LLM. It will finally generate this realistic. It will try to bring them closer, and this can be executed to have the final output. And you can see that it uses several of this existing models like DQA and some of the models like trim, crop, and evaluate. So this is the module list that our program can currently take. For video understanding, we have 6 modules, and you can see that these are existing state-of-the-art models for VQA and for tracking and for segmentation and summarization. So these models in red, they are the ones that are currently pre-trained models. You can replace them with any other better model if it comes out in future. And the models in the blue, these are just the trivial functions like crop, trim. They are just, we wrote those functions down. We try to accomplish 4 tasks in this work, which is VQA, video anticipation, pose estimation, and multi-video VQA. So in this example of the visual question answering, so if you look at that, the question is, what does the man do after entering the room? Here you can see that, okay, we can simply divide this question. We can break down this question into some more logical sub-questions, and we start with grounding. So we ground the video with man enters the room. We only extract the relevant frames using trim after, and now we only pass this final output of this video to the VQ module. So we don't essentially pass the entire video, we only pass the important part so the VQ model can focus more better. In the pose estimation, we follow similar steps for traditional work. They use these models like OpenPose and MMPose, and they have this skeletal representation. That's all they use. Using the following approach of visual programming, we use this approach of track and crop. These are the trivial functions that we use, and we pass this to MMPose, and based on some angle, for example, if a man is standing or sitting, there will be certain angles between the joints of his hands and arms. So that's something we leverage. So another example. And again, what happens when at the end of the video, if you look at the complete video, we start with trimming first, and then we detect the pose in this third row. And then finally, based on some angle calculations, we can do this fall detection. And this can be extended to crime hazard detection as well. Video editing is, again, another task that we can use some trivial functions like trimming, cutting, and adding visual effects and transitions. So using this VURF pipeline, we have divided into some easy steps. For example, in this color path, we do that on some extracted frames instead of the entire video frames. So essentially, when the model is just looking at the smaller part, it focuses more and works better in general. And this is multi-video question answers. So we have 2 videos, and you pass that same tracking query, and it uses some count functions to tell you how many number of people in the kitchen in the both videos. But again, you can use different functions. We did some experiments and we did some comparisons on as compared to the baseline. And as you can see that using our method, we have some trivial improvement based on some existing data sets, and we only test that on the validation sets of these models. And again, we also, the in-context examples that we have, we try to train the video chat GPT model on the top of the in-context examples we have, but we still see that the performance was limited to 22.3, but it's simple leveraging this LLM, we get it to 44.5%. All right, and this is the ablation study. We try to highlight that without this error correction and self-refinement model, which is the original performance, this is the performance we're getting in the top row. And with error correction, we get this, and with the self-correction, we get approximately a similar performance, but combining them both, we do have substantial performance improvement as compared to the base model without having nothing. So we will get some performance increments on that. And if you're wondering, when we discussed that how many times you have to pass the in-context examples to the self-refinement module, we found out that after 3 iterations, we generally try to, the trend try to flatten out, and we don't see much improvement on that. So 3 number of times is the right number of time to improve the in-context examples using the self-refinement block. Again, just to end the presentation, we have some qualitative results. And for example, in this, what color is the liquid in the beakers in the girl's hands, and then we have some visual program. Visual program has track. We apply track twice, and then you have march, graph, VQA. Right now in this, we have 5 steps, but eventually it can be more than that based on your query and based on the in-context examples and the reasoning capabilities of an LLM. And now, for example, in this task, you have to count the number of cars that are shown in the video. So you essentially trim to the essential part where you see all the cars, and then you apply the function of count. The count can use some existing models like segmentation model. You can replace that with that. So it's essentially just in plug and play model. All right, so we have one more example. You have to track a man in blue and blur the background. So you track that person who is in the blue, and then you essentially do some video editing stuff like background blur. That's the output. So essentially, in summary, we extend an existing work of visual programming that was done for images. We extend that for an additional modality, which is the video in this case. And we work for pose estimation, multi-video VQA, and general visual question answering paradigms. But again, it's not just limited to that. You can expand to more tasks by having your own interpreting that. It's a general framework. Again, you can use some off-the-shelf existing models. Whichever models you feel is the latest one, feel free to use them, and our framework will be able to let you use it. And the concept of self-refinement frameworks and multiple places, one for in-context examples and one where LM generates an output, we have essentially found out that that is something novel, and it improves the performance as compared to the base when you don't have it. So it decomposes a task with some implicit reasoning. So that's our work. Thank you so much. If you have any questions, please feel free to ask.
Awesome. Yeah. Thanks a lot, Ashmal. Appreciate your detailed walkthrough of the talk. So yeah, the audience, if you guys want to jump in here with any question, just unmute yourself and ask it. And in the meantime, you said the code is open source, right? So it'd be great if you can also put the repo into the chat for people to take a look.
Right. We did upload a partial code on that. We're still uploading the final versions. We're updating on that. So yes, you will. I'll post that in the chat as well.
Awesome. Great. Any question from the attendees? I guess one thing, so you mentioned a different downstream tasks, right? So from multiple choice video QA to pose estimation to video editing, right? What are the possible tasks do you think can also be solved with this framework? Or what do you plan to like add additional into the, which is that is a general framework you can do plug and play, right? What are the downstream tasks you're interested in exploring?
Right. So currently we are not expanding our list on that. So we're not currently actively working on that. But in terms of extending the number of tasks, for example, if you can think about segmentation tasks, and if you want to use some of the existing visual programming techniques and functions, so essentially what you want is to make the video focus on important things. That's exactly something that's happening in the video or your input query. And so as long as you can disregard the information that's not being used by your model, I think essentially something you can use the pipeline of the VURF.
I think in one of the slide that you mentioned, figure 4 of the paper on the different modules.
Correct.
So you leverage different pre-trained model, right, for specific tasks.
Right. So we did take some popular methods for that. For example, for VQ, we take Sevilla, and for tracking, we take Deva. So this is essentially the modules that we're using. So VQA, tracking, segmentation, grounding, summarizing, and the post detection. There itself a complicated task, but mainly when we talk about the task that we're solving, we only try to in this framework we try to represent visual question answering, video anticipation, post estimation, and multi-video. But the good thing about this is for video anticipation or for pose estimation, you don't need to have a dedicated model for that. Essentially, if for pose estimation, you can use this segment module that we have, or if you can use a tracking module if you have, or if you want to just summarize the video first before determining what's happening in this video. So in one of the example of the summarization, or video anticipation, we leverage the summarize module. So we summarize using video chat GPT what's happening in this video, and then based on some summary, we try to anticipate what's going to happen in the future. So these components can be used together as well.
Yeah, makes sense. Maybe one final question before we move on is around reasoning capabilities, right? So I think the key features of this framework is the GPT 3.5 ability to accept an input, accept like a natural language instruction and perform reasoning on what the sequential task they're gonna execute moving forward. It's almost like an agentic system, that can perform different activities, right? From editing to trimming to like segmentation, etc. I think what are you most excited about? Like what could be like the next limit, right, of reasoning capabilities? What are the other kind of thing like this framework can do, assuming the LLM become more intelligent, especially if you see like for O, right? With the test time compute capabilities, those kind of things. Yeah, just curious about your thoughts on this piece.
Right, right. So essentially, in general, I think that this work can be applied to many downstream tasks as well. So when you don't have, because nowadays, if you see that the entire focus has been on the scale of models, the new models are coming out with some specialized capabilities. And recently, there was also one paper which leverages this VQA and the segmentation models together. What essentially they do is they output this VQA or multimodals or VLMs output, and then they use for better segmentation, right? So essentially nowadays we have to combine multiple modalities to have a much better output, just like a image mine or language mine kind of concept. So I think the good thing about this VURF and the visual programming in general is that you can use multiple modules in your downstream task. So you don't necessarily have to stick to training a new model or get your data set for that. And as long as you can find a way to have this good in context examples, because one thing we noticed in our project when we were doing is it was very important to have this high quality in context examples, because GPT or any open source or LLM or this GPT-4, it does have this in context learning capability. But as long as you can have this right set of examples that utilizes the list of modules proper, you can ideally use this framework. And I think we also have one question in the chat.
Yep.
You said that, can I ask this kind of question? When did the woman drop the cup? Yes. So if you can track the woman in using some modules, using the tracking module that you have, and then you can try to capture the moment. For example, see, the entire part of this program is, the entire part of this pipeline is, we are not limiting to a certain task. If you feel that this task can be better handled by a VLM or some other model, you can simply have an interpreter for that and you can have it. But if on the top of VLM, you are doing some tracking and you're doing some cropping and you're trimming some frames of that, so you're essentially passing only the small part of the video instead of a full video. So VLM would be looking at a more nuanced perspective to only the selective frames. So it will generally not try to hallucinate by looking at the frames that are not essentially useful. So it's completely up to you, your task and the downstream task that you want to accomplish. I think you can leverage this pipeline.
So I have the follow-up question. So like, as you said, that we have to kind of like sample some frames to input the VLM model, which means that if I ask that, so what is the second, can you tell me the exact second that when the woman dropped, then maybe the model doesn't know, right? Because they don't have this kind of temporal knowledge in itself. So maybe they can say that in the end, like you can say, but they actually don't know like what the exact time that the woman dropped the cup.
Right. So you can also use this grounding module for that. That can give you the timestamps for exactly that. So that is something that we also do that. So if you can try to trim that certain portions, and if you can find the intervals for that, so you can use some existing methods and leverage off-the-shelf models for that. So we are not promising you a new VLM or kind of model. We're just saying that whatever the best model you have available, just use them along with some additional information, and that's going to make your output better.
Thank you.
You're welcome.
Awesome. Thank you, Ashmal. And if you have any more question, you can put on the chat. So Yujin, since you already unmute, do you want to go ahead and share your screen and present?
Sure. Can you see my screen?
Yes, I can see it.
Okay, we can go on. So hi everyone, my name is Yujin, and so first of all, thanks for the invitation today, and I'm happy to present our work. As James mentioned, my work that it is accepted to Europe's workshop, and recently it got accepted to Triple AI. So yeah, you can find out that one. So I worked this when I was doing the internship in Naver AI lab. It was really great opportunity for me, and so I want to present our work. It's about read, watch, and scream sound generation from text and video. So as you can see in the title, that it is about a sound generation model from text and video modality. So let's get started. So I want to first talk about our motivation of our work. I'm not sure how many guys you know about the Foley. So it is about this kind of like post-production like process to enhance the audio quality. So it's recording the sound effect which is aligned with the movie film. So that will be added to film, but the people always should make the sound which is really time consuming. So there has been some kind of like tries that they are trying to replace this human work with AI model. And then so there was some kind of work. So and there is second motivation of our work that, as you already know, that there is like Sora or VO2, this kind of like text to video generation or image to video generation model has been like showing really incredible performances these days. And the drawback of these kind of models that they don't have any audio. But if we think about the like industry of like advertisement or something, then there should be some audio sound which is aligned with this video. So without that, if we can generate this kind of sound that is really aligning well with this video, then it would be really great. So we thought about this kind of framework, that sound generation from video, or we can call it as video to sound generation. So there should be a video, and if it is going to the model, then it will generate the audio sound. So this kind of framework is like working like this. First, they identify what kind of like semantics that they should generate the sound. And then they should decide the temporal information when the like sound should be generated. So this kind of framework, there are two main baselines, which is SpecVQGAN and DeFoley. SpecVQGAN is for like transformer model, and DeFoley is like diffusion-based model. They are getting video as input and trying to generate the audio sound. So okay, let's think about this kind of video. What kind of like what kind of like sound should be generated from this? I think that so the dog is not really opening its mouth, so the barking sound should not be generated from here. And also real ground truth of like this kind of sound is dog growling. And these previous works are generating this kind of video, this kind of sound. So as you can see that like first one was only trying to just like capture what kind of like dogs like sound. So it's more like barking sound, and the Foley even fails to generate the sound. It is because the video actually has a lot of information in itself, and sometimes it just fails to capture the right semantics or right temporal information. So without that, maybe we need more controllability, or we need more like context to what kind of sound should be generated. So in our work, we kind of thought about this kind of frame. Okay, then if it is too hard the task, then let's just give a text as like, so we can capture some controllability, and there should be some off screen. We can just generate that sound too. And we can provide some context to text, which is easier for the model. And we are trying to give the video, but it is just for the temporal information that where the sound should be generated. So for example, we can give this kind of a text, and there can be some kind of this wave video. So the text is about the wave, peaks, like crash, this kind of information we are giving. And then the sound can be generated like this. So as you can see, like the wave sound and thunder sound was in the beginning, and then the wave crashes when and the sound was kind of grown bigger. And let's go back to the previous example that if we are giving this video and then we are giving the text at the same time, then now we can finally having the sound of like dog growling. Yeah, so it is our model, and this is the whole framework of how our model works. Let's break it down to two parts. That first one is control prediction, and second one is conditional sound generation. And I want to first talk about the conditional sound generation part. So as I told you before, that we are trying to give the text to what to generate. So we are giving lion roaring to generate the sound. So for that, we are bringing the text-to audio generation pre-trained model, which is AudioLDM. I think many of you already know the latent diffusion model, which is AudioLDM here. So for AudioLDM, we are giving the text prompt, and then for that, we can generate the sound based on this text condition, which is like trained on a lot of like data set, which is Lion audio set, I think, and it so can take a lot of like general text prompts to generate the sound. So we took this pre-trained model for the better performances. So we are getting the pre-trained model for getting the text to generate the sound. Then what about the video here? That we have to incorporate video information in our text to video generation, text to audio generation model. So how we do it is like this energy adapter. I will talk about the energy a bit later. So you can just think of like energy right now as just video information. So to incorporate the information of video, we were thinking about the contour net. I think many of you already know the contour net is like, if we have the diffusion model, we can get some like freezing some pre-trained parameters, and we are just like train only this additional adapter parameters so that it can incorporate another like contour, like this kind of edge in image domain. And so that we can generate these aligned image generation. So in audio generation part, what kind of like information should be given? For example, we can just give some kind of like volume information that you should generate the audio sound like this. Then we can generate some kind of Merz spectrogram to look like this. Then what kind of this like information we should give? And this is the energy that I was talking about, and we will talk about it a bit later. That is the contour prediction part, and we will go to there. So I talked to you about the energy. So what is that? It's a variable spectrogram on the frequency axis, which is really, you can think of just like volume of the audio here. And without that, this kind of energy is actually really aligned with the video. Because if we think about the lion rolling video, if it opens up the mouth, then we know that the movement is bigger there, and then we can know that there should be the bigger sound. So actually from video, we can actually predict that kind of energy from the video. So for that, we were using MSA loss to train this energy prediction module to predict the energy. And we kind of got this kind of results so the first row is ground truth energy, and second row is about the video energy that we predicted. So we can put this predicted energy to generate the sound. So we have these two parts, and only we can train this kind of energy prediction module and additional energy adapter. So which means that we only train really few parts, and then we are bringing the pre-trained model which already perform very well, so we can get some effectiveness and efficiency at the same time. So if we compare with the other baseline, our results are comparable. And then if we see the training parameters in the last column, that ours are fewer than others. And also in sound generation part, the human evaluation is really important because like people should really listen and then really need to tell if it is like natural or not. And we got the best score in this. And why do we need the text prompt for video or video to audio generation? We analyze more because there are many real like noisy videos in the real world. And so you can see in the picture that like it is about actually chicken clerking, but you can see it's a kind of cartoonic in the beginning, and then there is even the redundant like video frames in the end. And then if we are just giving it to the video to audio model, then like they are kind of like confused that what kind of like sound should be generated, and they are just making the random sound based on this video. But we can give chicken clerking, then it can find where to generate the sound better. So ours only can generate chicken clerking sound in the beginning. And there is more demo of, I can show you why we need energy. As you can see, we only gave the text prompt the car engine, but in the end, like, you kind of heard that there was the spray sound in the video. So why is it happening? We wondered, and then we got the hint that the energy actually conveys more meaning than the volume. So if it just the model takes the energy, and if it sees some kind of tendency, then they know even that people are kind of like speaking or there is a spray sound, so they kind of detect this kind of information too. And also we can actually input more kind of general prompt, like a chef is cutting onions in the kitchen preparing for the dish. So you can see more demos in our page. So for the summary, our ReWaS, which is our model, is a strong generalization and strong temporal alignment for visual content because we use energy thing for the temporal alignment, and it is really efficient training because we only trained only fewer parameters compared to other video to audio generation models. Thank you for listening, and then this is our page, and then you can talk to me in my email too. And yeah, if you have any questions, feel free to ask me. Thank you.
Awesome. Yeah, thanks, Yujin. This is great. Very interactive presentation. Very cool demos.
Thank you.
Yeah. Any question from the audience about the model? I guess I have one question. Maybe not a question, but more just curiosity about. I think it's super cool that you come up with the concept of energy prediction. That basically like the gap from the content prediction to content generation, right? Like that is the layer that allows you to like capture what you call energy from the video and then use that to dictate how the sound will be generated. I just thought that is a very interesting approach, and I haven't seen any other work that can did that modality integration of video and audio that novel. Yeah.
Thanks for saying this. So like this energy control has been like kind of explored in only text to sound generation part, that like people were wondering what kind of like control they should give. And so we try to manage that, like maybe from the video we can predict the energy from there. But actually I want to also mention that we thought that there can be more controls too. Like for example, like the pitch information, maybe we can get some kind of that kind of control too from the video, but actually it was really hard to kind of like get those kind of pitch information from the video. So maybe energy was the really just intuitive control that we can get from like video and audio.
Okay. And I think you mentioned a little about control net, right? That is the inspiration for how you control the audio, the energy. I mean, sorry.
Sorry.
sec.
Sorry, I couldn't hear the question. Or was it not a question?
No, it was a comment on my end.
About the control net. Okay.
Control
Yeah.
net, yeah.
Yeah,
Okay,
maybe there is a hand that is raising from
Yeah.
Anya.
Yeah, I think he put the question on the Zoom chat if you want to answer it.
I see.
Yeah.
How the there's questions with multiple sound sources. Okay, so that is really good question that like we wondered like how the like if we are just like saying only like if there are multiple objects, then how can we do? And in the last month, I showed that there can be some kind of spray, and if there is some kind of like people and the dart, then we kind of generate the people sound at the same time, even if we are just giving like generating the dart sound, so they can do it. But of course, if we are giving like really, really complex object with a lot of like background and a lot of like objects are given, then I don't think like our model can do that. But I think the other video to audio generation also fails. So that is really good point, and we have to tackle that point. Yeah.
All right.
So the scalability, okay, so we are now can generate 5 seconds of audio sound, but actually we can actually do the 10 seconds too. So it actually really dependent on the text to audio generation model. If it can generate like 20 seconds, of course we can do it too. But it is we are built on that framework, that pipeline. So we are actually like generate the moment that like they can generate.
Mm-hmm. And in this scenario, you're using AudioLDM, right? Text to audio. Is that the SOTA model for text to audio generation?
It used to be. Right now, there's AudioLDM 2. I think that is the new SOTA model, but I don't think like they released the weight or something.
I see. Awesome. Well, thanks a lot, Yujin. If I have any more question for her, just put on the chat. And yeah, then you guys can follow up and learn more. With that, Diji, do you want to go ahead and share your screen and go ahead with your presentation?
Hey, can you see my screen right now?
Yep, that's it. Go ahead.
Cool. Yeah, so yeah, we are short in time, so I will keep this quick. So hello everyone. First, thanks for the invitation. And my name is Diji, a PhD student from UC Santa Cruz, and I'm going to present our work, dual model distillation for efficient action classification with this hybrid edge cloud computing solution. So, and just a heads up, today my presentation will be more from the research perspective, but actually our original preprint is kind of like an application-driven project, so there might be some gap. Yeah, let me get started. So a little bit about the background. As many of you know, large vision language model, or LVL in short, now achieve very decent performance in many video text or image text benchmarks. But actually deploy those models into smart devices, those on devices deployment is quite challenging because those models usually include billion level of parameters, and the computing is kind of very slow on like small devices like cell phone. So there are two standard solutions kind of form the basis of our work. One is edge cloud computing. So the intuition is very straightforward. For simpler task, system calls the on-devices smart cell phone stuff, and this is very lightweight. And for the complex task, system calls a larger model, which is more powerful, and we deploy those models on the cloud devices. So as you can see, the goal is to maximize the performance while reduce the cost, or we can say reduce the number of large model call. And this standard approach, this simple versus complex strategy kind of requires system to know the difficulty of the given task in real time. And this is also very challenging because from the cognitive science perspective, the difficulty is actually subject to the individual's knowledge. Some tasks may be very easy for you, but it may be extremely hard for me since we have different background on knowledge. So both questions I listed here are hard for the case if we want to define a rule for it. So another related concept is about knowledge distillation. We consider that people consider background, those are existing works, consider the larger model as a teacher model and a smaller model as a student model. Then we can use a larger model to generate some synthetic data to supervise a smaller model to learn. But this approach is kind of broadly used in many scenarios, but there's a limitation that student model can really hard to match the teacher's model's capability due to the size of the parameters, no matter how good the distillation happens. Those background kind of motivate our final goal. We want to build a deployable solution to under this edge cloud computing scenario to decide the timing of large model call. So that we can, the goal is to optimize the performance while reduce the overall computing cost. Or in another word, if we assume larger model is better than smaller model, then we only call the larger model whenever smaller model cannot handle the given question. So to achieve this goal, we propose to train a model implicitly learn the question difficulty with considering the both models' capability. So now the problem is more clear. We need data for that. Because we don't have existing data to provide those capability information. So motivated by that, we propose this DMD algorithm, do model distillation. And let me explain it at concept level first. So the underlying technique is still knowledge distillation, but unlike the traditional methods, do model distillation treats both smaller model and larger model as the teacher models. So there are two teachers, and they co-teach a student model. In our case, we call it a switcher model. And now the idea become teacher model first generate synthetic data that includes their knowledge. Then for the switcher, training on this data set is a procedure to learn the capability of both teacher models. So after training is done, the switcher now can have a good sense of what each model can do and what they cannot do. Okay, now let's not dive into more detail to see how this algorithm, do model distillation algorithm works. So first, for each data set, for each data point from the data set, of course, the training set, we run zero-shot inference using both large model and small models. Then we assign the label based on result. So if both model provide the same answer, then it's a agree. Otherwise, it will be a disagree label. We also record the verdict for smaller model. If the answer is correct, then that's right. Otherwise, it will become a wrong. And then we can format the data in this way. So the input is a task content plus a prediction from smaller model plus a smaller model's last hidden layer. And the label will be just agree or disagree plus right or wrong. So using this data set, we can now train a classifier, or we call that switcher, to decide whether we should call for the given question, whether we should call the larger model or not. So specifically, we call the larger model only when switcher predicts that the large model is very likely to disagree with smaller model, and the smaller model's prediction is very likely to be wrong. So in our notation, it's a disagree plus wrong case. And this is our system design from our report, but it's kind of outdated as we are keep updating the system. So I will skip this one and use a more conceptual design to present our pipeline. So during the inference time, so here the cloud refers to GPU service provider, and the edge devices refer to smartphone and smart camera in our case, which usually cannot serve a model larger than maybe 2B or even smaller. So at the inference time, after the switcher is well trained, the task input first goes into the small model and gets a prediction. And based on this prediction and the last hidden layer representation of the smaller model, our switcher is able to make a good prediction based on two major things. One is this prediction is bad? And if so, will the large model disagree with it? So if still a yes answer, then system will call the larger model for a prediction and send that to user as an output from the whole system. Otherwise, the system will directly use a smaller model's prediction as a whole system's output. And yeah, as I mentioned before, this work originally is an application-driven project. So our application domain is not those very hot CV tasks. It's about falling detection in healthcare domain. We did an evaluation on this fall detection data set and other our internal data sets. And the task is just a simple binary classification task. So the goal is like given a short clip, model need to identify whether a falling is happening or it's just normal daily activity. So as you can see, this is kind of important use case in healthcare domain, and a lightweight on-device computing is kind of a necessary requirement for this task, because we cannot just install a very powerful machine in all senior people's house to ask for help if they want to send some alert to health provider. And yeah, for our implementation, we use a relatively small vision language transformer around 500 million parameters as our smaller model. We apply some domain-specific fine-tuning for this small model, and we use a LavaNext video version, a 7D version as our larger model. Also, we train a very lightweight MLP with just 2 layers. It's pretty easy to train as our switcher. So for result, we mainly report 3 metrics. One is F1 score. This is very standard evaluation on this dataset, nothing special. And we also report the percentage of the test point, dataset point, that like the percentage of test set were processed by the large model. So as you can see, small model in small model only setting, 0% of data goes into the large model. And for our system, the switcher choose to load 60% data onto the large model. And we also report the execution time for the whole data set. So for the result, we can see that although small model is extremely fast, but the prediction result is kind of unacceptable in such a critical, result sensitive, accuracy sensitive task. And we show that our system can achieve much more better result compared to the using smaller model only. And due to less number of large model call, it reduces total execution time. Besides, another interesting thing is our system also have decent improvements above using large model only. So this is pretty good because we didn't apply any fine tuning on both large and smaller model. So recently we conduct some ablation study and analyze on the failure case. We find that each model has their own specialties. So for some data point, smaller model can do better than large model, and our switcher model captured that. And because of our training objective for switcher is just to optimize the final accuracy. So it learned to only call the larger model when it thinks smaller model really cannot handle it. So for the case, even that a switcher think a large model will disagree with smaller model as long as the smaller model prediction looks good enough, the switcher won't call the large model for those data points. And yeah, just want to quick mention what we are doing right now. We are kind of testing our system on more standard task, CV task and data set, and updating our pipeline to support more models. Also, we are working on deeper analysis. Yeah, I guess now it's time to conclude this work. A few things I want to highlight. The first is as our DMD algorithm generated data contains knowledge of both model, we really want to highlight that this is targeting a very critical research problem. On one side, the knowledge alignment across multiple models is pretty important under this agentic age. Like people are arguing everything is can be agent, but the optimization on the collaboration between multiple models or agents is still under studied. Also, as you may know, some good researchers, they are arguing that large model pre-training used all or almost used all the available data. So unsupervised or semi-supervised method to generate synthetic data brings more opportunity. And you can, like, with a very cheap price and resources, you can get a good amount of synthetic data. And another thing is that this is a very user-friendly framework and no heavy fine-tuning needed on VLM. And also access to the large models weights is not a requirement. So that user can use some good performing closed source models via API access, like ChatGPT stuff. And finally, the training of the switcher is extremely lightweight. Even you use a free version of Google Colab, you can get the job done. So yeah, I think that's all the content. And again, this is ongoing work. So if you have any suggestions or comments, please let Timothy or me know. It will be really meaningful for us. And yeah, I guess I'm ready to take questions.
Awesome, yeah. Thanks, Diji. This is super exciting work. I think it's definitely have a very real, have a huge real world application, right? Especially for instances where you just, you cannot leverage a large model. I think just having that low cost saving in inference would be great. In your previous slide about the ongoing work, right? You do my go to your previous slide. I think you mentioned more models. Yeah, this one. Yeah. Can you share a bit more details? What the data set, what models are you considering for future directions here?
Yeah. Actually, yeah, I can share a little bit detail because from this existing work, we only focus on video to text modality. So it's a classification task. But actually, as long as we have a good evaluation matrix, we can do this DMD algorithm. So that means even in some, text to image, like text generation framework, we can still apply our method to first do some distillation and let the switcher to decide, okay, this prompt is easy, so I'm gonna call a lightweight image generation model. And if the prompt is very complicated, it will call like a larger diffusion model, some similar thing. So yeah, that's cross modality is our main focus for ongoing work.
That's good. Kyle, do you want to unmute yourself and ask your question?
Yeah, sure thing. Really cool work. Super cool stuff in here. I wanted to ask, do you think that this approach could be extended to perform like a mixture of experts type configuration where you have a bank of switcher models that you trained up and then a bunch of experts essentially that request gets routed to?
Yeah, I do think that's possible. That's that's definitely a interesting future work. And the pre-request, still, as I mentioned, is a good evaluation metric. So you have to use the DMD algorithm, you have to know what kind of output is a good output and what is a bad output. So as long as we can meet that pre-request, yeah, we can apply to MOE framework, definitely.
Awesome, thank you.
Great. Yeah, so I know we about 10 minutes over time, so probably gonna conclude the webinar today. Yeah, thanks again, Diji and Yujin as well for presenting today. Recording the session should be available by early next week, so I email you guys when the link is up on YouTube. Yeah, thanks again for the attendees for attending, and we have a lot more research presentation over the upcoming Friday of the webinar. So you found this informative and interesting, yeah, subscribe to our channel and stay up to date with future session. Thanks everyone, and hope you have a great rest of your weekend. Bye bye.